So my name's Scott Schurr. I'm here to talk about constexpr applications, and you didn't know it when you walked in, but you're walking in on a sales presentation. My goal with this presentation is to give you reasons to care about constexpr, that it's not just some oddball word that somebody tossed into the language for no particularly good reason, that there are actually situations where if you think about it a little bit, this keyword can help you out. I learned about constexpr fairly late in the development of C++11. I was watching other stuff and I thought that was cool. And then all of a sudden this kind of constexpr slipped up on me and I said, oh wow, I've been doing embedded development for years. And constexpr allows you to do stuff at compile time. And this is, to me, the kinds of things it will allow you to do, I think are pretty darn amazing. So I don't want you to hold your questions. I like an interactive session. I think it helps keep everybody more awake, including me. Yeah, it's the afternoon. I reward participation, and I have here the reward. I'm from Portland, Oregon, so I like rewards that are biodegradable. This is as biodegradable as it gets. It's chocolate. I work for a company based in San Francisco called Ripple Labs, and strangely enough, San Francisco also has Ghirardelli chocolate. So if you have an answer for me, because I'm not an expert, I'm just a dude, if you have an answer for me or if you have questions or whatever else, not only do you get to ask your question or make your statement, but you also get chocolate. So with that, let's go. So the point is, yesterday I talked about the rules behind constexpr. Today, why would we bother? And if you attended the talk yesterday, I'm going to do a little bit of review so that people who weren't there can catch up. But I'm going to try to go pretty fast through the first, say, 20 slides, and then we'll slow down and deal with containers. So we have a new keyword, constexpr, introduced in C++11, and you can have constexpr values, and you can have constexpr code, functions or constructors. Constexpr values look like this. You can have a constexpr value at namespace scope. You can also have a constexpr function or value at function scope. And you can also have a static data member of a literal type of a struct or a class or whatever. So those are all valid places to use the constexpr keyword. What you get out of that is a value. If you use the constexpr keyword in those kinds of situations, you have a value that is known at compile time. Okay, does that surprise anybody here? Am I going too fast? Cool. So, because this is, we're doing yesterday's presentation in about 3 minutes. So, constexpr computations, which is the flip side of that, you can have free functions, member functions, constructors. The code that's allowed inside of those functions or constructors, once you attach that constexpr keyword to them, that code is very constrained. It's extraordinarily constrained in C++11, and the rules get relaxed a fair amount in C++14. And because we allow constexpr constructors, that allows you to define a literal type, something, an object that can be known at compile time by your compiler. So we're going to do a quick walk through compile time parsing, which was something I covered yesterday. Actually, let me quickly ask, are there people in this room who were not here yesterday? Okay, so I should not go too fast here. Okay, so I'm going to leave some of the details out that I included yesterday. But we're going to talk through a C++11 binary literal. How many of you, I do embedded code, I wanted binary literals for years, for decades. And in C++14, we now have them. In C++11, you can build your own, okay? So there is no native binary literal in C++11. Can we make one? Using constexpr, the answer is yes. This is it. That's the whole thing. No template trickery. It's C++ code. Yes, it's recursive, but it's C++ code. Yes?
Quick question. The meaning of throw in a constexpr function?
Okay, this is great. So thank you. The question was, what is the meaning of throw in a constexpr function? And there are actually two answers to that question. Constexpr functions the value can be computed at compile time. The result of that constexpr function can be computed at compile time. But you can also invoke a constexpr function so that it runs at runtime. They run in both circumstances. So depending on the circumstance, you get two different results from your throw. In one situation, when you have your throw, if it's at compile time, you get a compile error. Okay? So the compiler will stop you, and you have to figure out what caused the throw to occur. Once you fix that, so this is, again, from one of the things I covered yesterday, is this is a single expression. The entire piece of code there, that's a single expression with sub-expressions. And so as long as, and this is a C++11ism, as long as the sub-expression that contains the throw is never evaluated, the compiler just turns a blind eye and says, nah, I don't see that. If it has to actually execute it at compile time, this is, oh, now you made me face this. I really have to deal with this, but I don't know how to. I'm going to stop. I'm going to get some guidance. If it's at runtime, you get the throw. Okay? So, how do you use it? This is an example of how you would use it. It's a binary literal. I gave it a long name. It doesn't have to be that long a name. One of my coworkers gets really annoyed with the length of my names. And it's also worth noting that we've got static asserts in there. So I hope most of you are acquainted with static assert. Any of you who are not acquainted with static assert, you must become acquainted with static assert. It's more important than constexpr. It's easier to use also. Yeah, so those are all compile time values. In C++14, the rules get relaxed quite a bit. And hopefully there'll be a video of yesterday's, and if you care about some of those rules, I go through that. So in C++14, it's easier to code, not quite as useful because there is a binary literal. And this is the way you would write the code in C++14. This has no recursion. There's, if your standard, this is maintainable code with a capital M. Your standard C++ developer walks in and sees that code. They know exactly what's going on. And this allows you to do compile time computations. We're not doing template metaprogramming. This is maintainable code. Another quick thing from yesterday, or a couple of quick points. What are some limits on constexpr? And this is from Annex B in the standard. There are two parts of the annex that describe limitations in constexpr implementations. They suggest C++11 constexpr lives on recursion. So they recommend a minimum recursion depth of 512, which will get you a long way. And then particularly in C++14, and I hope to get into some more detail on this, the minimum number of full expressions that are evaluated to produce a single constexpr value in C++14 is in excess of 1 million. We'll talk about some stuff where 1 million may not be enough for some circumstances. But it's worth knowing that 1 million seems like a lot, and it is a lot. It will get you a long way, but it may not get you to everywhere you could possibly imagine. And these are recommended minimums. So it's really up to your compiler. So I said earlier, constexpr can either run at compile time or at runtime. And so what happens if you get an error, a throw, for example, at compile time? And in this particular case, we've misused the binary literal. We left a space in the middle. And so what does that error look like? This is the kind of error you would get from Clang. I don't know what Visual Studio or GCC would produce. And so this is maybe worth talking about. The way you force a constexpr piece of code, method or function, the way you force it to be computed at compile time is to force its results to be a compile time thing. And the easiest way to do that is to have the result of that computation go into a constexpr variable. So you'll notice right up there on mask, mask is declared as constexpr. That's how we're forcing it to be a compile time value. Everybody, yes?
Does that make mask a constant, or just initially evaluate compile time and you can reassign it later?
It is absolutely a constant. Okay. Yeah, constexpr values are implicitly const, and if you cast away that constness and then modify the value, I learned yesterday, and then modify the value, you are definitely deep in the unspecified behavior, or whatever. I just picked the wrong word. But it's a bad place to be. Don't go there. This is a constant. Don't cast away its constness.
So is there a way to have a default value assigned at compile time, but then be able to change it down the road? Or would you need two variables, one that was the constexpr, and then below it you'd have the
So the question so the question is, I think, whether you would, once you've established this constexpr value, can you change it? If you did, how would you deal with changing values? And the answer is that a changing value can't be a constexpr value. So if you want to compute a value ahead of time that's constexpr, once it's that constexpr value, it will not, you may not change it. So you would have to have another variable someplace and then copy it into that other variable, and then you can thrash all you want.
It would have to be static for it to be initialized.
This gentleman says it would, a static might serve that purpose. But if it's a static constexpr value, then you can't change it, right?
Then you can or can't.
If it's a static constexpr value, then you cannot change it.
Yeah. Okay.
Right. Okay.
Question.
Yes.
I'm still new to this constexpr keyword, so I'm wondering how would it be different as opposed to just labeling the variables or whatever values as const, and have the compiler to try and evaluate those values by default in compile time?
Yeah. So if they were const, then you don't have any guarantee that the compiler knows what they are. So if you compute a runtime value and assign that to a const variable, it was still determined at runtime. So, and if it's determined at runtime, you can't do a static assert with it. Okay, so that's really the difference, is that if it's constexpr, the compiler knows what the value is. And it's also constant. Okay, and I'm going to let some, could you pass that chocolate back? Sure. Thank you. Did I? Oh, well. Okay. So we left off the constexpr. That's why we're going to get a user error at runtime. And that's what it's going to look like. We'll get a throw. Now, the problem to me is that, at least for this particular situation where we're trying to do a binary literal, the likelihood of us wanting to determine that at runtime is pretty low. You know, you might have a situation where somebody's passing a string in and you want to do that, but that's really not the point of this particular exercise. We want it to be a compile time kind of a thing. Yeah, I won't go into debugging. So we've got two different cases where we're determining a binary literal, and they both have errors, and one of them is going to lead to a runtime error, and the other one you will catch at compile time. So which one's which? Any guesses? Yeah.
The first one is compile time, and the second one is runtime.
Nice, nice. So, and chocolate. So the answer is the second one is the one that's going to be a runtime error. That's going to throw.
Does the second one preserve constants? Like,
No,
would the auto that's returned there, would it be constant?
no.
Okay.
Thank you. So the question was, will the second one be const? And the answer is no. A similar question is, if you have a constexpr function and you do an auto of the return from a constexpr function, is that auto a constexpr? And the answer is no. You still have to force it to be constexpr. The compiler resists you forcing it to establish something at compile time. You really have to be insistent. Yes?
And decal type auto would just come across as const?
Well, decal type on the function?
On the variable.
Oh, on that
The auto variable on mask B.
Oh, no, it won't even come back as const. It'll come back as, so the question is, if you did a decal type on mask B, what would you get? And what you'll get is a uint 8t. Chocolate.
Sure. Thank you.
You're welcome. So the thing I don't like about this is that every time you call that function, every single one of those calls is an opportunity for a mistake. So we don't like mistakes. We want to try to make things easy to use. And is there a way to force this? And the standards guys did a lot of cool work with constexpr, but for whatever reason, there isn't a way that I'm aware of within the standard to force a constexpr function that can only be evaluated at compile time. Nevertheless, there's a hack. Howard Hinnant helped guide this particular hack. So we can put an unresolved symbol in a throw. So we've talked about how if you can have a throw in a constexpr function, and as long as that throw is not evaluated at compile time, you can just leave it there. So what we're going to do is we're going to have an unresolved external, and we're going to reference that unresolved external in your throw. What's going to happen with that? You're now going to get your user errors at link time. It'll look like this. It's not very pretty, but it's the best I can do. There may be someone who's got a better answer, and if there is someone, I hope they will tell me, because I'd like to hear it. Yes?
What about making a wrapper function where the wrapper function assigns the result of the real function to a const expression local variable and then returns that value?
Yeah, so that was actually suggested to me last spring by a fellow that used to work in the Visual Studio compiler before it was became more compliant with C++ 11. So one of the problems is that you can't declare a constexpr parameter on a function. So if you declare
As a local variable inside the function.
yes, so but if the constexpr anyway, it doesn't work. So this is the only one I'm aware of that works. Why does it work? So the throw, if we're evaluating compile time, we skip the throw. So we don't notice that the symbol's missing. If we have a runtime implementation, the runtime implementation has to include everything because you never know when it might need to throw. And that means that you're going to run into your unresolved external. Well, like I said, this is not pretty. But, oh, yes, and one more point. It may not work. Richard Smith, who is the brains behind C++, or constexpr in C++ 14, pointed out that even though the compiler and linker may be inclined not to include the throw, they're still allowed to include the throw. So I'm not going to guarantee that this particular workaround is going to work for all circumstances. It could depend on your compiler, it can depend on your linker switches or whatever. So you can force stuff to be included that would retain your throw, and then what you would have would be a false positive. Did you have a question?
I was just going to ask, then it's compiler dependent whether you're using, say, GCC or Clang or DC.
Right, yeah, so this has worked great for me in my test cases in Clang. Yeah, and it's going to be compiler dependent. I believe that most compilers are inclined to not include code they don't need. Okay, so this is going to work most of the time, but I'm not making any guarantees for you. And it is the best I can do for you. So the summary is you have a constexpr function with a throw. Sometimes you have to invent the throw situation, count something that you didn't actually need to count. You declare an unresolved extern char star, and then you reference it in your throw. So in terms of compile time parsing, I think it's an interesting technique. The applications are limited, but it's not just a binary literal. There are other places where you can compute literals that are useful. And in general, you're going to see repeatedly, consider the unresolved extern hack, because for me, a lot of the functionality of constexpr is in stuff that I know I want at compile time. So let's talk about containers. This is a big container, and it doesn't change very much. So if you have a constexpr container, as we were saying earlier, that's a const container. Do any of you have situations where you have containers that you have all of the information for how you would put the container together, but nevertheless, you end up at runtime stuffing a bunch of things into a vector and then sorting them, or stuff like that? Does that happen? Yeah, okay, I'm seeing some nods. So that's the kind of situation we're going to talk about. We're going to have constant containers. You're not going to be able to, at runtime, you can't force anything more into these things. They're set in concrete by your compiler. Nevertheless, I think this is a particularly useful situation. We're going to use arrays. And then the question is, why bother? So any errors you have, those errors are going to get caught at compile time. There are situations where you'll get improved code readability, and I will hopefully guide you into those. Yes?
Does attempting to add additional elements to this array, is that interpreted as an error at compile time?
Could you speak up?
Is attempting to add additional elements to a constexpr array interpreted as an error at compile time?
So the question is, if you attempt to add values to a constexpr array at runtime, will that produce a compile time error? And the answer is yes, because the thing is constexpr, and so when you try to modify it, the compiler will yell at you, as long as you don't cast away its constness, which you please don't. Oh, yeah, and somebody pass this chocolate back. So we're going to reduce the executable footprint because we no longer have to sort that container at runtime. And we don't have to deal with global ordering issues with these containers, which is something that I've had a lot of headaches with. And we don't have thread races because the values are known long before anything starts running. So let's come up with some actual use cases for these things. Well, okay, we can just declare an array with some values. Now, we're just starting to stick the nose of the camel into the tent. This is nothing exciting other than the fact that we can put the constexpr keyword on there. You could do this with a static const array, basically the same functionality. But let's hypothesize a function, a constexpr function that we're going to call constexpr sine. What we now have is an array of sine values. We have if you're doing signal processing, we now have 10 parts of a sine wave. And historically, the way you would solve this problem is by typing in a bunch of floating point numbers. And so you have this array of 10 floating point values. And if somebody comes in to maintain this, if there isn't a nice comment up at the top that says, this is a sine wave, if you just stare at it, you're going to say, what in the heck is going on? So now we can compute the sine wave at compile time and put the results in the array. So again, you have to take my word that constexpr sine is computable. But take my word for that. I've done it. It's not fun, but you can do it. It's self-documenting, and it avoids typos. So if we're going to advance further on constexpr containers, we're going to want to be able to return a constexpr array. What I found was that oftentimes the return array was based on the size of the input. So I'd hand in, say, a bunch of char stars, and I would get back a container that had as many elements as the char stars came in. So using a little bit of template trickery up at the top, or the size tn, to determine the size of the returned array. It turns out this is very close to standard array. What I had to do was I tossed in a few more constexpr keywords than are provided in C++11. And by the time you've tossed in those extra constexpr keywords, a standard array would do all the work for you. Question in the back.
Kind of sounds like a bug in the standard array definition. Do you know if anyone's been discussing that?
So the assertion was that it sounds like a bug in the standard array standard definition, and that could very well be the case. I haven't talked to anybody about it, but it would be interesting to walk through some of the use cases that I have for this. And I think by putting constexpr in the right places, that a standard array would do all this work for us. Yeah, yeah. So you want to send this chocolate back? Thanks. So, and there's another hand in the back. Oh, there's Beeman. Yes.
My memory is, and Howard may have a better memory because he's here, but I believe at the time we put constexpr in, we were doing it as a thought experiment because I don't think any of us had a compiler that actually implemented it.
Fair enough. Yeah. So.
And so, yeah, there's probably a lot of mistakes.
Yeah. So.
No except is not the same situation exactly.
Yeah. So Beeman, who's on the standards committee, was just saying that there are probably a lot of places where because they didn't have compilers that supported constexpr. Thank you. They made their best guess about where should we toss in the constexpr, and yeah, there'll be stuff we're learning. So anyway, now we have a type, which is an array that we can return from a place, and we can determine its size by the size of an array that gets passed in by doing template tricks. And not very hard template tricks. You have to be comfortable enough with templates to do this stuff, but this is not hard template stuff. So T, which is what we're going to put in our array, it's essential that T has a default constructor, because constexpr requires that. Basically, the way the compiler computes a constexpr value is by running a C++ interpreter. And to save the brains of the C++ interpreter, it insists that every value that it ever deals with, anywhere along the way, that it always knows what that value is. So the declaration of T data underscore n, that's going to default initialize everything in the member data array. So if you don't have a default constructor for T, or a basic type like with an int, yeah, there's no official default constructor, but it will zero initialize because of the braces.
Or if you don't initialize the variables inside that constructor.
So, right, if it weren't an array, you could initialize, if you initialize in the initializer list, then you're golden. But everything has to be initialized for an object type. Everything has to be initialized before you get to the body of the constructor. Yes?
Does your type T need to have like a constexpr constructor?
Yes. Either that or it has to be one of the native types which are effectively constexpr.
But you have to prepend it with a constexpr expression on the constructor.
Well, so yeah, so every constexpr object, or every object that goes into a constexpr object must also have a constexpr constructor. So interestingly, there's motivation for having constexpr functions that are not const. We'll get into this in more detail later. But one way I think about it, this really shows up in C++ 14. I don't know that it plays as much in C++ 11. But when you pour your concrete, it takes a little while for it to set. And we'll get to the model. When you're constructing in C++ 14, when you're constructing your array, there's a while where you get to play with the contents. That's really important. So the contents of your array can change until you return it to the constexpr value. Once it hits the value, then you're locked in. It's no longer mutable. It's a question of when it becomes finally, when the C++ interpreter finishes with it, is when it gets locked in place. So we do have non-const constexpr functions. And we're going to use those, we can only use those before the value gets returned. And the compiler will help us with that. So we had this array of values and we were filling in by hand generate sine all the time. And the nice thing about that was that if you misspelled generate sine, the compiler would stop you. But it's still a lot of handwork. So wouldn't you rather have a function that would return to you a table of a sine table for you? So here we're going to make ourselves a sine table. We're going to get called with a size, how big a sine table do you want me to make? And then we're going to fill in the values by calling constexpr sine. So getting to the non-const values, we're going to initialize our result. That defaults everything. And now we're going to walk through the elements of that local array. We're going to modify them. We can only call constexpr functions, but we can, using those constexpr functions, we can modify the contents of that array. And now we're going to return it. When it's returned, that's when the concrete sets. Right now, I'm talking about C++ 14. If we were working in C++ 11, we'd be doing a lot more work. Because in C++ 11, you can't put anything in the body of the constructor.
Question?
Yes.
What compilers are supporting that now? Is Clang and GCC?
Both Clang and GCC support C++ 14 constexpr. Visual Studio does not. Visual Studio is now at pretty complete support for C++ 11 constexpr. But Clang and GCC are both at C++ 14.
Isn't VS15 pretty close?
They're very good with C++ 11 constexpr right now. I think they have a long way to go to, so the question was, where's Visual Studio on this? And I'm not a Microsoft guy, okay. but they've just clawed their way up to having C++ 11 support for constexpr.
One that they can't forward declare constexpr functions, which is a real pain in the butt. You've got interleaving dependencies between your constexpr functions.
Yeah, okay, so.
Because they don't do two-phase lookup, essentially.
Okay, so what Howard's saying is that they don't support constexpr forward declarations, which is a pain. So let's see, we've seen all this stuff, we've seen that stuff, and this is where we're going to try it. So now we have a compile time sine table is generated by a function that computes our sine wave. As long as that function works right, we always get the right answer for floating point and right.
So the bottom, you're just trying to do one at runtime, one at compile time?
Yeah. So it's just, this is kind of a toy, but you want to exercise a little bit. Yes?
So if you have a const expression function, which means that it's being evaluated at compile time, why do you need to specify const expression for the variables inside that function? Wouldn't they also have the requirement of being evaluated at compile time?
Yeah, so the question is, if you have a constexpr function, do you need to declare the variables inside that function as constexpr? And the answer is no. So those variables don't need to be constexpr, but the functions that are called from a constexpr function, those functions must be constexpr. So when you're in a constexpr constructor or function or whatever else, it's allowed to call outside. But if it calls outside, the only places it is allowed to call is to another constexpr function. So it's this chain of, can I be computed at compile time or not? So, but the local variables, actually, you can get yourself in a lot of, some trouble by trying to declare constexpr functions or constexpr values inside of a constexpr function.
So you could dump the constexpr from line 3 and be functionally equivalent?
Yes.
Thank you.
So the question was, can you dump the constexpr from line 3? The answer is yes. No.
Isn't that the only thing that forces generate sine to be constexpr in this case? You should get a file error, I would think, if you
Yeah.
constexpr.
And at this point, I'm going to have to say I'm not a good enough compiler in my brain to have a confident answer.
Okay.
Yeah.
Honest. Thank you.
So in this particular case, so I was thinking of the previous case where I'm going to modify the values. And this is in sine lookup, and I'm not going to modify those values. So in this case, I don't know that I have to declare it as constexpr. Again, I'm not a compiler. In the earlier case where we were calling generate sine, its value cannot be constexpr because you're going to be modifying it before you return it. So, yeah, sorry. You already have chocolate, right?
Yeah, I'm doing all right.
Okay. So, okay, I think that was a pretty cool example. What are some other things we can mess with? Well, a lot of these compile time tables have text in them. So can we convert text to, say, all uppercase at compile time? Yeah. So here I've got one of my favorite architects because we're talking about buildings, sort of. Can we convert that to uppercase? So it's going to print uppercase. And the thing I think is magic is if you go dig into the assembly language that's produced, there is no mixed case Frank Lloyd Wright, at least what Clang produced for me. The mixed case Frank Lloyd Wright was not present in the resulting object file, only the uppercase. So this leads me to believe we can do some interesting stuff with text at compile time. So just to recap where we're at, we've computed array entries, we've generated an array, we've returned an array based on input that we got at compile time. Yeah, okay. If I made an array, can I verify at compile time that that array is alphabetical? Well, we need a way to compare these things, so we need a less than evaluation. This compiles and works. So now we can walk through, if we get a pointer to the beginning of a list of char star and a pointer to the end, so we've now got our iterators. If we get a pointer to that list, and now we can walk through that list, and we can return true or false based on whether that value is, or whether that list is alphabetical. And this is done at compile time. So now, say you have a significant sized list, more than 4 entries. You have a bunch of these guys in some file, and you want to make sure they're always alphabetical, even in the face of maintenance, because this is easy to do when you're making that list initially. But you got dudes walking in there saying, oh God, we got to add another architect today. Yeah, let's get that in there. Okay, we're going to run, the compiler says it's not alphabetical anymore. So we've got some real leverage for finding errors at compile time, because it's a static assert.
So I have
15
a question.
minutes.
I was just thinking, can you go back to us one
Yeah.
second?
Yeah.
So you have the count 4, and you also have the 4 things here. Suppose we make the count 6, and then we add a 5th string, and one of them is null because we forgot to put 6 things and we have only 5. So now we have a null there.
Yeah.
What is going to happen here with the at compile time? Because that would be a runtime, right? If we have a null, we try to compare a null with a.
Yeah. Well, and that's so. The question is, what's the if because I'm setting the count, and if let's say that somebody set the count to 6 and only put 4 entries in, there would be nulls in the array.
Right.
And so what would happen? And the question, the answer to that is, how does your string compare deal with those nulls?
Oh, the string compare would, well, in a real world scenario, we try to dereference the pointer, no? In other words, you have a null
Yeah,
pointer.
so, right.
So the string compare would blow up.
Yeah, so, and so if the string compare blows up, then that will be a compile error.
Okay. So a suggestion might be, just this is completely off topic, but instead of saying count for count, suppose you left the count out of the picture and made the count the size of the array, and then let the number of elements guard that.
Right, and so the advice, which is excellent advice, the advice is to leave the count out altogether and let the array determine its own size. And the reason I put the 4 in had to do with ease of putting the count in the right place.
Oh, you can
for
put
the
the count
pointer.
afterwards and take the size of the array, you'd be in business.
Right, yeah. So, but this, yeah. So, thank you, John.
Would it even compile if you didn't have enough elements to completely fill?
Yeah, it will compile. It will compile. If you say I have an array of 8 and you only put 4 elements in, it will fill in the rest for you. So okay, we had somebody who we had a compile time check to say, is this an alphabetical array? Can we get the compiler to do the sort for us? Well, I probably wouldn't be asking that question if I didn't have the answer that I wanted to give you. Yeah, let's let the compiler do the sort. And this is a cheap sort. This is about as cheap as sorts get. I did an insertion sort because the code's really easy and it all fits on one slide. But don't feel constrained. You know, if you've got production code, you don't have to do an insertion sort. You can do a more complicated sort because you'll have more lines of code to write. You can do that. You don't have to fit on a slide. And that static assert is just kind of gloss on there. So this is interesting. That sort has a void return type. And in C++ 11, that's not allowed. But you can get away with it in C++ 14. And I kind of hinted at that earlier on. There's that void return type. So a void return type on a constexpr function is useful in C++ 14 if it's not the outermost constexpr function. So for those few of you who were in yesterday's presentation, I had this picture up. This is kind of the C++ interpreter model I have in my head. It probably has no basis in reality. But this is the interpreter model I have for C++ 14. So that once you crawl inside function A, which is our outermost constexpr function, function B, C, and D all know that they're producing constexpr values. So they all have that same context. So the inner calls, B, C, and D, can return void. So now we can do our string sort. Yes?
If you declared A or something, and you evaluated A, and then on a separate line you re-referenced the value of A, and would you not then be able to sort or change it? Is the constness established once the value is finally saved or at the end of compilation?
The value, so the question is when does the concrete set?
Yes.
Yeah, and the concrete sets when you're finished with if you're declaring a value A as constexpr, as soon as the compiler is done with that line, the concrete is set. You can't now at compile time go modify A. It's when you walk away from A, it's done. The cookies are baked. So let's sort these at compile time. So one of the questions would be, well, why don't I always sort these things at compile time? I have 10 minutes. So we won't get to floating point, but we'll spend some more quality time on containers. So the validation is going to be faster than the sort. And that has to, so you're going to care about your compile time. There are also limits on the number of I'm going to get the phrase wrong, but basically the amount of code that your C++ interpreter will allow you to compile to determine one value. So if you insist on having the compiler do the sort, you'll run out of headroom sooner than if you just do the validation. But it's up to you. You can make your choice, which is a nice position to be in. So, your call. So, all right, can we do an associative container? Well, okay, we can make a sorted vector and have that stand in for an associative container. Well, we have a sorted array now. Huh. Okay, so if we add more iterators or more, we're basically going to add iterators to our return array type so that we can do more bouncing around in there. We can now call equal range on our return array type. So you build a sorted array at compile time, and at runtime, you can now access that as though it were a set by doing a binary search. So we're going to find the value. Everything happened where it needed to be. So how about a hash container? This is way out on a limb. So hash containers are hard. It's a much bigger stretch. You would have to be really dedicated to want to do this. Partly because of how standard hashing works. Yes. Could you speak up?
Dense hash map, which is open hashing, and then you reserve around 4 times the space until you're done, and it's a continuous vector case.
Right. So the point is that you don't have to do standard hashing. You've got hashing options. I'm not a hash container guy. Okay. So this was, somebody asked me, could you do this? And so I just stuck my nose into hash containers enough to pull something out. An expert could really go to town on this, I suspect. So I gave it my best shot, which is just barely useful, maybe. But I think it sets the tone for, this is not outside the realm of possibility. So we know all of our, at least the way I solve the problem, we know all of these values at compile time. You know, if we're hashing strings, those strings are there. So if you know what those values are, thank you, you can, as a person, you can go through, or you can have a program that goes and looks at those things and comes up with a perfect minimal hash. That means that the values will be, the hash values will be contiguous. And there will be no collisions. So now, when you get your strings in, you can compute the hash value. Put your hash value and your string in place in your array. So yes, we need a struct to hold the two values. We've got a hash value and we've got a string pointer. So this is the container for that. And we give it a less, because you can't use lambdas in constexpr in C++14. There is a proposal for lambdas in constexpr lambdas in C++17. So we're going to fill in the hash container. Then we're going to sort it based on the hash value. And then at the end of the function, we're going to verify that the hash really was minimal and perfect. And this was my hack. I was looking for a hash function, and so this is one I found manually. And it only works for those 4 strings, of course. But we now have a 4-element hash container built at compile time and validated at compile time. So, container downsides, okay, they're immutable. The call site has to know the container size because you're returning an array. It has to know how big that's going to be. So if you're, the way I solve that is if I'm making a container that has 4 string entries, I'm passing those 4 strings in, I'm going to deduce the size of the return value based on what's coming in. And the templates will do that for you. So you have to watch out for the evaluated expression limit or the recursion depth limit. And you can't put a string in there because strings require new. And that irritates me. String view, at one point I thought was going to help with that, but it sounds like string views are now becoming mutable, which means that I have to find some other salvation. So let's summarize that, and I think I'm about out of time. Thank you. So constexpr containers can be validated at compile time, prevent initialization race conditions, reduce your code footprint, and in C++14, this is pretty close to natural. And the lack of the string support is awkward. And accidental use at runtime can be bad. So consider the unresolved extern hack. So time's up. I did this presentation last spring at C++ Now, except I did it in a different order. So the floating point will hopefully sometime fairly soon be available on YouTube. Is the end of the presentation on constexpr at C++ Now last spring. So if you're really dedicated and curious and willing to put up with that, the information will be available there. And the slides for the floating point side of things will be available. So, but we don't, I'm really actually delighted that we got all the way through the container stuff. So, let's see, I have some thank yous to toss in at the end if I can get to those. Show navigator. There we go. Yeah. So Gabby did constexpr for C++11. Richard Smith did constexpr for C++14. Scott Myers is always great. I rely on him. Howard Hinnant figured out the unresolved external for the hack. Thank you very much, Howard. Friend of mine did the slide review. Constexpr text came from CPP reference. Biquad code, which you would see if you saw the floating point side of things, that came from a particular website. And the errors are mine. Okay, thank you very much.